So we have a 1 kilogram block, which means I've been given the mass, that's attached to a spring in simple harmonic motion on a frictionless surface, and we have the position x as a function of time. And we want to know the period of the oscillation. So period is defined as the time it takes for one full oscillation. So from this amplitude down to the negative, up back to the same amplitude would take 1 second. So the period is 1 second. And then your frequency is 1 over the period. 1 over 1 just gives me a frequency of 1 hertz. And remember, the definition of frequency is how many waves you get in, or how many oscillations you get in a single second. Well, in 1 second, I get 1 full oscillation, so that makes sense. To find the velocity at 0.25 seconds. So if we go to 0.25 seconds, that's at the equilibrium point, or where x equals 0. So that means potential energy is 0, which means it's all kinetic energy. So you're basically asking, when all of this potential energy goes into all of this kinetic energy, what would the speed be? So we're going to use the potential energy at the start, so at t equals 0, going in, that's t equals 0. That doesn't look like t equals, but you can listen. Is going to go into all kinetic energy at t equals 0.25 seconds. So now we're going to plug in, this is 1/2 kx squared, that's 1/2 mv squared. We can cross these offs. Oops, we need k in order to find your velocity. But I have a relationship given just what I know to find the k, because I was given mass and I know the period based on the graph, so I can use my period is 2 pi square root of m over k equation, plug in 1 second, oops, not s, equals 2 pi square root of mass of 1.5 divided by k. And then, first thing we need to do is get the square root by itself, so I'm going to divide the 2 pi over. And when you're dividing this 2 pi over, be super careful in your calculator, because, hold on, let me make it so you can see. So when you're typing that, dividing like this is going to give you a totally wrong answer. You need to do 1 divided by parentheses 2 pi, because that's telling the calculator you want the 2 and the pi both on the bottom getting all divided. This is 1/2 of pi, not the same thing. So then you get this equals square root of 1.5 over k, and we want to square everything, so we'll get rid of the square root. By squaring equals 1.5 over k. Your unknowns on the bottom, you have to multiply this up. So then you have k, 0.02 equals this, and you divide the 0.02 over. Well, hopefully this is totally not needed, but just in case. And then that gives me my k is 59.22. So now I know my k, and now I can go back and use that to find my velocity. And once you find your k for your spring, you don't need to find it again. It's a spring constant. It's going to be constant as long as you're keeping the same spring. All right, so k is 59.22, and then our x squared, so we're talking about all potential energy. That's at the very, very beginning. So you just want this x right here that you started with, which if this is 0.5 and it's going up by 0.1, that would be 0.8 meters. So 0.8 squared equals mass of 1.5 v max squared. I'm just going to label this v max because this is not just any velocity, it's the velocity at equilibrium at 0.25 seconds when it's all kinetic energy. So then you can divide the 1.5 over and take the square root, and you would get that your maximum velocity is 5.02 meters per second. And now it is just going through and figuring out at each of these times, like, is it my maximum, is it the minimum, etc. So 0.25 we said was the maximum. This one is actually going in the negative direction, so it is going the maximum speed, but if you imagine this as like the positive displacement, if it's being pulled to the right and released, that's the max velocity when it's going to the left, so a negative velocity. So this would be negative 5.02 meters per second. And then at 0.5 seconds, right here, your velocity is going to be 0 at this maximum displacement, because this is when it goes from negative into a positive velocity. Between negative and positive, you have to pass through 0. It has to stop for an instant to turn around and go the other way, so velocity would be 0 here. At 0.75, this is again at equilibrium. It's going to be that maximum speed, but now it's going in the positive direction, so that would be positive 5.02. And then at 1 second, you are again back at the maximum amplitude, the maximum displacement right before it turns around, so you get your velocity is going to equal 0 at that point. Hold on, my computer keeps thinking about this. It's killing me. Okay, so the next one, we want to know the acceleration at different points. So let's go to 0.25 seconds. 0.25 seconds, you're at the equilibrium, which is when x equals 0. If you're at equilibrium, your net force is 0, so you have 0 acceleration. Now if I go to 0.5 seconds, that is where I'm the furthest from the equilibrium. I'm going to have the greatest force at this point, which means I'll have the greatest acceleration. So first thing to think about when you're solving for acceleration is, okay, well, acceleration comes from a force, F equals ma. So then divide your mass over, and then you have that your acceleration is just the net force over the mass. That's true for any case. In this particular case, when we're talking about a mass oscillating on a spring, well, the force, the net force when it is at any position, is just going to be the spring force. Because if you were to draw the free body diagram of like this when it's stretched, you would have, of course, the force of gravity, but then you'd have normal, so those kind of cancel out. And then you just have the spring force, whether it's stretched or compressed. If it's being stretched to the right, it'll feel a force back towards equilibrium. If it's being compressed to the left, then it'll feel a force back towards equilibrium the other way. Okay, so I'm going to replace my net force with my spring force, and the spring force is just kx. So kx over m, and then at 0.5 seconds, that is at the maximum amplitude of 0.8. So you can plug in the 59.22 for your k, amplitude of 0.8 over mass of 1.5, and that's going to give me my acceleration is 31.58. If you want to check units. And then direction can be kind of tricky, because what people will want to do is just put in, okay, I have a positive displacement, or we're at 0.5. I have a negative displacement, I get a negative acceleration. But if you look at your equation sheet, the force equals kx actually has absolute value signs around them, which is not saying that they're always positive. It's saying that these don't have to have the same direction. We don't know how this direction relates here, but they don't have to be the same. So now we just think about it. So if this is being stretched or compressed in the negative direction, it's going to feel a force back towards equilibrium, which would be like in the positive direction or up on your graph. So that means your acceleration is going to be in the positive direction, so that would be a positive. And if you're in calculus, your acceleration is like the second derivative of the graph, so this is concave up, so that's like a second derivative is positive, meaning acceleration is positive. If you're not in calculus, totally ignore that. At 0.75 seconds, you're back at equilibrium, force is 0, so acceleration would be 0. And at 1 second, that is my maximum displacement, so I'm back to my maximum acceleration, except for now that I'm in the positive displacement, my force is back towards equilibrium, which is in the negative direction, so negative 31.58. Alright, the total energy in the system. So I always think about total energy as like, what is the energy it started with? So this was all potential energy at the beginning, 1/2 kx squared, and then my k, I know. And then the x at the beginning was 0.8. So that's going to give me my potential energy at the start is 18.9 joules. Now you also could have done kinetic energy. The maximum kinetic energy is 1/2 mv maximum squared, and that would be 1/2 of 1 times 1.5 times 5.02 squared, which is again going to give me 18.9 joules. Now what you don't want to do is add these, because some people are like, oh, total, that's both the kinetic and the potential energy. Yes, that is true, but this is the maximum potential energy and this is the maximum kinetic. There is no position or time where you have both the maximum this and maximum that. Here you have 18.9 joules of potential. Here I have 18.9 joules of kinetic energy. But when I have this much potential, it started from rest, so K was 0. If I have this much kinetic, well, I'm at the equilibrium, so I have no potential energy here. So the total is still the 18.9, and at any other point, at all of the points, these two together will combine to that total of 18.9. So my total energy is just the energy it starts with. Kinetic energy at 0.25, well, this is where it's going the fastest. There's no potential energy, so this would be the total. At 0.5, that's the farthest away. It's where velocity is 0 for an instant, so kinetic energy would have to be 0. And then What would follow, we don't need to worry about, oh, is it net positive or negative? Yes, this one is going in the negative direction. It has a negative velocity, but when you have v squared, negative squared becomes positive. So energy does not have direction, so don't worry about that. And then you can think about your potentials just the opposite, because they have to add up to the same total. So if this is 18.9 and the total is 18.9, this one has to be 0 and vice versa. You also can think about it as your potential energy depends on x, so it's 0 when it's at the position x, so 0.5 and 0.25 and 0.75. And it's at the maximum when it's at the maximum displacement, so at the 0.5 and 1 second. Velocity of the block when it is at position 0.5 meters from equilibrium, so we're going to use conservation of energy. So this is all potential energy at the start goes into some potential and some kinetic at x equals 0.5. So the 1/2 k 59 x at the beginning, which was 0.8 squared, is going into 1/2 k x at this point that I'm asking about squared plus 1/2 mass v squared. You can cross off all your halves because there's a half in every term, and then just rearrange. I'm not going to show you how I get this. And that gives me that the velocity is 3.92 meters per second at this point. And this at least is reasonable because my maximum velocity is 5.02, so I knew it had to be somewhere between 0 and 5.02. And then at 0.5 meters, or position of 0.5 meters, it's, somewhere in the middle, not quite halfway, but somewhere in the middle of the velocity, so this is reasonable. Alright, average speed. So we know that our velocity is changing the entire time, your acceleration is changing the entire time, so when we talk about average speed, that we're just going to say, on average, what distance does it travel in what time. And you can do a lot of different times. You can't do just like a single millisecond, but you could do like this half. You could do the full graph. You could do one full oscillation. As long as you're doing the distance that corresponds with that time, it doesn't matter. So I just did like this section right here. It's going from 0.8 down to negative 0.8, which means that the distance traveled would be 1.6 meters, and then it took 0.5 seconds. So 1.6 meters in 0.5 seconds is going to give me an average speed of 3.2 meters per second. Which is the same as if I used okay, let's look at the full oscillation. It took 1 second. I went down 1.6 meters and I went up another 1.6. So that's a total of 3.2 meters in a single second. Oh, I get the same average speed. Okay. The period of a pendulum, so that's the t equals 2 pi squared of L over g. It depends on the length of the pendulum, and it depends on little g, which is the acceleration due to gravity. So like on Earth, your acceleration due to gravity is 10. When I go to the moon, it's something else. When I go to Mars, it's something else. So if I go to a different planet where that has a different acceleration due to gravity, then my period will change. For a period of mass on a spring, that only depends on the mass and the spring constant of the spring, K. Amplitude has no effect on the period of oscillation for either one. This is just stuff that we've already kind of talked about in the front. What do each of these devices measure? Meter stick measures the distance. Motion detector will give you position or velocity or acceleration, and they typically create position, velocity, and acceleration graphs. A balance is going to tell you the mass of an object, and a photo gate will tell you the speed of an object, and a stopwatch will tell you the time. If an object has the same size but a greater density, then what do you know about that? That it has a greater mass. Same size literally meaning measured radius or measured size. But if this one is denser, then it has a greater mass. Right, we have a displacement graph, and we're looking at 1/4 t. So if this is t, this is half t, this is 1/4 t. So this would be 1/4 t right here. So at this point, this is at the maximum displacement. My velocity is going to be 0 here. You can think about it as the velocity is the slope of the displacement graph, and that's a flat slope between positive and negative velocity. And then my acceleration is going to be at a maximum. We have to be careful with your sign. when it's being pulled in the positive direction, it's going to feel a force towards equilibrium, towards the negative direction, so its acceleration is going to be negative. So I want velocity equals 0, which crosses off B and C. This is saying A greater than 0, which is positive. I want A less than 0, negative, so that's why D. A block of mass M is attached to a spring of spring constant K, and it slides on a frictionless table with a speed of V max at equilibrium. What is the maximum amplitude of this spring? So this is saying it comes in mass with some V max, and then this is like the equilibrium, and then obviously it gets like some sort of, I don't know, compression. This is a weird drawing. I don't like this. This looks so bad. I guess stretch. Anyway, it really, this is a terrible drawing. I'm going to stop drawing. You have V max at the equilibrium, and then when it's at the maximum amplitude, it's being like stretched or compressed the entire amount. So all of your kinetic energy goes into all potential energy. So you have 1/2 mv max squared equals 1/2 k. I'm going to call this like the amplitude squared. You could call it x maximum. That's the same thing. Halves cancel out. We're trying to find the amplitude, so divide k over. And that's I'm gonna go down here. mv max squared over k gives me a squared, so take the square root. Now, you have a squared inside of a square root, so the v max can come outside because the square root of the square just cancels out. But the m and the k cannot come outside because they don't have squares, so then you're just left with v max times square root of m over k, which is d. Object swings on the end of a cord as a simple pendulum with period t. Another object oscillates up and down at the end of a vertical spring with period t. If the masses are both doubled, then what happens to the new periods? Well, for a pendulum, it's 2 pi squared of L over G, so increasing the mass has no effect. So, oh wow, that made it really easy. I only gave you one option that had t staying the same for the pendulum. So that tells me the answer. But we can also talk about why this is times root 2. So for a mass on a spring, 2 pi square root of m over k, if you double the mass, that's like putting a factor of 2 right here, which doesn't make this twice as big because it's inside of a square root. It makes it root 2 times bigger, which is why B. A pendulum is released from a height of 0.3 meters, and then it swings, and when it comes back, it only reaches 0.2 meters. And we want to know what explains the decrease in this maximum potential because it's not reaching as high as it should. The energy transferred into kinetic? No, because yes, it transfers into kinetic, but at the time where you're reaching the high up as it goes again, then the kinetic is 0. So what's happening is it's losing energy to outside the system. So this would be like air resistance, the same way like if you include friction, right? It's losing some of its kinetic and its potential energy. So in this case, outside the system, if you're just thinking about Earth and the pendulum, it's losing energy to like the air molecules around it. That's the idea. 0.5 mass attached to a horizontal spring of spring constant 800, so I have m and k. It's stretched this much from the spring's equilibrium point. It is then released and oscillates. What is its speed through equilibrium? So what is its maximum speed? And this is the amplitude. So when it's stretched, it's holding all potential energy, and then through equilibrium, potential would be 0, so it goes into all kinetic energy. So I've got 1/2 kx squared goes into 1/2 mv squared, halves cancel, k is 800, x is my maximum x, because at the beginning that biggest amplitude, or biggest displacement, which is called the amplitude, equals mass v squared, and then let's see what I got. You get that v squared is equal to 4, so take the square root, your velocity would then be 2 meters per second through the equilibrium. A pendulum with a period t is taken to a planet with the same mass as Earth, but with triple the radius. What is the new period? So think about your period equation for a pendulum is 2 pi square root of L over G. So you're keeping the same length because it's the same pendulum, but if I go to a different planet, then I might have a different G. Okay, so I'm telling you I keep the same mass as Earth, but I triple the radius. So look at your equation for little g. It's on your equation sheet, like on the bottom. So gm over r squared. So like for the acceleration due to gravity for some planet, it depends on our constant g, the 6.7 whatever, times mass of the planet divided by the radius of the planet squared. So if I keep the same mass, but I have 3 times the radius, then that's going to give me times 1/9 the original, the original acceleration. So instead of L over G, this is now becoming L over 1/9 G. Okay, so we've decided that we have a smaller acceleration due to gravity. If you're dividing by a smaller number, that's going to give me a longer period. So we can cross off the same, because it's going to be different, and we can cross off the ones that are getting smaller, because I know my period gets longer. Now, this is inside of square root, so that factor of 9 actually becomes a factor of 3. Now, if you're wondering, wait, you have 1/9 on bottom, how did you get 3? Well, we have the square root of 1/9 on bottom, nothing's happening on top, that's 1. 1 over 1/9 is the same as 9, so then the square root of 9 is 3. Or another, that's easy to make a silly mistake and just forget the 1 on top and put 1/9. So an easier way is, okay, I'm dividing by a smaller number, that should get bigger. Cross off, oh, it's square root, it's really a factor of 3. Right, a pendulum is taken to a new planet and the height above the equilibrium of the pendulum as it oscillates is shown to the right as a function of time. Which of the following additional pieces of information would be needed to calculate the acceleration due to gravity? So you're saying, what would you need in order to calculate G? So the only equation that has G in it really is this one right here. So I have the time, right? This has a period right here. So I know this, and you're trying to find this. That means the only other thing you need is L. So you would need the length of the pendulum. And what is the frequency of oscillations? Well, frequency is how many waves you get in 1 second. So in a single second, not waves, I keep saying that, oscillations you get. So in a single second, you're only getting part of an oscillation. But the easiest way to think about it is just 1 over the period. And if you look, the time for one oscillation is 20 seconds. So 1 over 20 seconds is going to give me a frequency of 0.05 hertz. A pendulum oscillates with a frequency of 0.5, and I want to know the length of the pendulum. So I can use my period equals 2 pi L over G equation. If we're talking on Earth, that means that we can use G as just 10, -9.8, but for AP we just use 10 to make it simpler. But that means I need to know my period. Well, if you have your frequency is 0.5, and period's 1 over frequency, 1 over 0.5 gives me a period of 2. So now you have 2 equals 2 pi square root of L over 10 for G. Divide the 2 pi over. Make sure you put parentheses in your calculator. Then we're going to square everything, and then that's going to, did I show my work? Oh yeah, I did. 0.101 equals L over 10, and then you're going to multiply the 10 up, and that gives me 1.01 for my L. So the best answer is 1 meter. Pendulum is released from a height and oscillates if the same pendulum is released from the same height, but now has a greater mass on the end. How would the following values change? Well, when we look at period for a pendulum, that's 2 pi square root of L over G. So there's no dependence on mass, so this is going to stay the same. Maximum potential energy. Maximum potential energy, it starts with gravitational potential energy, which is mgh. If you're on the same planet, you're keeping the same g, you kept the same h because it tells me if I increase the mass, then you're increasing this, so this would increase. Maximum kinetic energy. So if you're starting with more potential, then that means you have more kinetic when it is turned into all kinetic because energy is conserved. The maximum speed of the mass. Let's think about, in terms of energy, using energy, we can come up with an expression. So I start with all gravitational. At the bottom, when it's going to maximum speed, it's all kinetic energy. So I've got mgh would go into 1/2 mv squared. M's cancel out, multiply your 2 up, so you have 2gh is v squared, so v is the square root of 2gh. So the maximum speed only depends on gravity and it depends on the height. So if I keep the same gravity and the same height, then my Vmax should stay the same. It has no dependence on mass. For those of you who are like, wait, but there's more kinetic energy. Yes, that is true. You have more kinetic energy, but you also have more mass. So the more mass is why you have more kinetic energy, not because your velocity changed in this case. On average speed, that's just distance over time. Well, changing the mass, but releasing from the same height is going to travel the same distance, right? The same height and back again. and it's going to take the same amount of time. So if you do the same distance in the same amount of time, then you get the same average speed. Sorry, this probably doesn't look like words, but you can hear me. And then frequency. Frequency is 1 over period. So if I keep the same period, I keep the same frequency. A pendulum is released from a height and oscillates. If the same pendulum is released from a higher height, how would the following values change? So you're basically changing the amplitude. Period of oscillation is the 2 pi square root of L over G. You haven't changed the length of the pendulum, you've just changed how high you release it from. That's not the same as length. This is just the amplitude, so no dependence on amplitude, so this is going to stay the same. Maximum potential energy, well, I start with mgh. You just increased h, so you definitely just increase the maximum potential energy. Maximum kinetic would have to go up because, again, the kinetic energy here just comes from the potential energy at the beginning, so if this increases, then this increases, because your total energy increases and total energy is conserved. The maximum speed of Vmax, so we came up with the expression Vmax is the square root of 2gh. So if you increase h at the beginning, then you're going to increase the max speed of the object. Average speed is distance over time. So we know that it's the same time, but think about if I have a pendulum that goes from here to here versus a pendulum that went from like here to here. These are not good pictures, oh god. Okay, this is my pendulum, and it goes from here to here, so it goes this distance. If I release it from a higher height, then it's going to go to a higher height over here, so it's going to travel a greater distance in that same time. So if you have a greater distance in the same amount of time, that means it's going faster, so your average speed has increased. And then your frequency. Again, frequency is 1 over period. If period doesn't change, frequency can't change, so this stays the same. 14, we've got a mass on a spring and it oscillates on a frictionless horizontal surface. If we increase the mass, what would that do? So now we're talking about mass on a spring, so that's the 2 pi square root of m over k equation. If I increase m, that means I am increasing the period. Because this is a direct relationship, well, directly related to the square root, so more mass on top would give me a longer period here. Maximum potential energy, so I'm starting with spring potential energy, 1/2 kx squared, where x is like your amplitude. Increasing the mass is not going to affect my spring constant or how far I've compressed it, so this has to stay the same. Your maximum kinetic energy, 1/2 mv squared. Some people are tempted to go, okay, well this has dependence on mass, so more this, more that. Well, I was able to say that here because I knew that k stayed the same. K is the spring constant, and it didn't say anything about changing the spring constant. So this increased and this stayed the same, so it had to go up. You can say m increases, so kinetic energy increases, only if v stayed the same. And we don't know that the velocity stayed the same. In fact, I'm actually looking in the next question to see if velocity stayed the same. So we have to be careful here. So we think about, okay, where did this kinetic energy come from? It came from the potential energy we started with. We're starting with the same potential energy as before, so we'll have the same kinetic energy as before. Which now brings us to what the velocity was doing. So we know that this value, this kinetic energy, has to stay the same, and we know that this mass increased. So if this mass increased, but I keep the same kinetic energy, that means this maximum velocity had to decrease because this increasing and decreasing would balance out to keep the same kinetic energy. Or you can think about it, I still have the same total energy, so the same kinetic energy, but now for a greater mass must be going slower. Otherwise, more mass would mean more kinetic energy. So my Vmax is going to decrease. You also, just like we came up with an expression before, we can do the same thing, except for now it's spring energy going into kinetic. 1/2 k x squared equals 1/2 mv squared. Halves cancel out. If I'm looking at the maximum, this is just like my amplitude. Divide m over, and then take the square root. So Vmax is just the square root of ka squared over m. Sorry, that's super messy. So you'll notice that this is a inverse relationship or indirect relationship. M is on the bottom, so when you divide by a greater number, this will get smaller. The acceleration at the maximum displacement, so it's F equals ma, right? And then we're looking at acceleration, so that's F over m. And my force that I'm looking at is the spring force, kx. Oops, not a, m. So the acceleration at any point is just the spring constant times where I am over m. The maximum displacement, or sorry, the acceleration at the maximum displacement is when it's like at the amplitude, the biggest x there is, the amplitude. So if I have the same k and a as before, because all I changed is mass, when I divide by this greater number, I'll get a smaller acceleration. So the acceleration of the maximum displacement should be decreasing. So you can think about it, your force doesn't depend on the mass, right? It's just k times the amplitude. So if I have the same force but over a greater mass, I'll get less acceleration. Average speed of the mass, so that's distance over time. It's still going the same distance because I haven't changed the amplitude. All I've changed is the mass. So if I release it from some point, it's still going that same distance. So this is staying the same, but now you're doing it in a greater amount of time, which means that it's going slower on average, or that your velocity, your average velocity has decreased. And then your frequency. So frequency is 1 over period. We know that we have a bigger period. When I divide by a bigger number, I get a smaller frequency. A mass is attached to a spring and oscillates on this horizontal surface. Now I'm going to increase the amplitude, so you're increasing A. What would that do to the period of oscillation? Well, period of oscillation is 2 pi m over k. So increasing A is going to do nothing, it will stay the same. Your maximum potential energy, that's 1/2 k amplitude squared, or kx squared, where x is the amplitude you started with. So if I am pulling it a greater distance, then it's definitely storing more potential energy at that point, so that would definitely increase. Now kinetic energy is 1/2 mv squared, which doesn't have a dependence on A, but you know that your kinetic energy, or your energy, is conserved. So this kinetic energy at the maximum kinetic energy point is just the potential energy from the beginning, so it has to increase as well because there's more energy in the system. And then the max speed of the mass, well, we came up with this equation. V max is the square root of k squared over m. So if I increase A, then I'm increasing the maximum speed. So this is going to go up. Another way to think about it is you just increase your kinetic energy. So 1/2 mv squared. This is staying the same, but this increased, so that means that this velocity must have increased. And your acceleration, so we said that the maximum acceleration is ka over m. So again, direct relationship, if you increase A, you're increasing the acceleration. Or you can think about it, you have a greater force over the same mass, so more acceleration. Average speed, so increasing the amplitude means you're doing a greater distance, so you're going a greater distance, because instead of just A to like negative A and back, now you're doing a greater A to a farther negative A and back, so greater distance, and it's still in the same amount of time. So if you go farther in the same amount of time, that means you're going faster, so that your V average increased. And then frequency is just 1 over period. Period stay the same, so your frequency would have to stay the same. 16. A force of 5 newtons is required to pull a spring 8 centimeters from equilibrium, a block of 0.5 kilograms. So this is my force, this is my displacement from equilibrium. I'll just call this x for now. This is my mass, is then attached to the spring, and the spring and the block are released from rest. So this is like the maximum displacement, let's call it A. And I want to know the velocity of the block when it is this far from equilibrium. So at the beginning, it's starting all potential energy. And this is at like the start, we're at x equals 8 centimeters. And then it's going into both some potential and some kinetic at x equals 3 centimeters. So that's going to be 1/2 kx squared equals 1/2 kx squared plus 1/2 mv squared. Cancel out the halves. Now before I can plug in, I need to know my force. Not my force, sorry, my k, my spring constant. But I can find that if I know the force required to go to this x distance. Because if F equals kx, then I can plug in F, use my x to find my k. Now we need to be careful because in physics, right, if we want all of our other units to work out and my numbers to work out, we have to use our standard units. Our standard units for x or amplitude or distance is going to be in meters, not centimeters. So I'm going to have to convert 8 centimeters into meters, which is just 0.08 meters. And then this would be negative 0.03 meters. If you're wondering how I did that, just divide by 100 or divide by 10 squared to get to the meters. Because if I wanted to go from here to centimeters, I'd do times 10 to the negative 2 like it says on my equation sheet. Right, so then the force there, or the X that goes with the 5 newtons force is the 0.08, so I'm going to divide and I get my K is 62.5 for my spring constant. And now I'm ready to plug in, so 62.5, at the beginning that was the 0.08 squared, and then this is going into some potential and some kinetic, so I still have the same spring constant, but now I'm at the 0.03 position. I left off my negatives. You can totally keep it there, but you know when you square a negative, it's going to become positive, so I just left it off, plus the mass, 0.5v squared. And now it's just putting this in your calculator, subtract over, divide the 0.5, take the square root, and you should be getting your velocity is 0.829 meters per second. So the graph here shows the force exerted by a spring as a function of the length of the spring. And the spring is compressed until its length is 5 centimeters, and I want to know the potential energy stored at this position. So I would use 1/2 kx squared to find the potential energy stored at that position. That's pretty easy. So that means I need to know k and I need to know x. Now it's super tempting to say like, oh, this is my x. This is actually not my x. This is the length of the spring. Remember, x is defined as displacement from equilibrium. So if you look at your graph, you should be wondering, okay, which of these distances corresponds to equilibrium? Well, by definition, equilibrium is where your force is 0. So then the length of, what is that, 7 centimeters is equilibrium. So if my length is 5 centimeters, then that means my x, or my displacement from equilibrium, this is not x. Oh, cross. I'm saying this is not true. Okay, just turn into a bigger x. So then my x at 5 centimeters from the equilibrium, which is 7 centimeters, is just a -2 centimeters. So again, we have to be super, super careful, because what it's giving us here is the length of the spring, which is not the same as equilibrium. Equilibrium is like it's unstretched, or it's like no force position. So when the force is 0, that has a length of 7 centimeters. So if it's normally 7 centimeters, and I squish it to where it's only 5 centimeters, then I've displaced it -2 centimeters. And the negative just means I'm compressing it 2 centimeters. If it went to 9, it'd be positive, but it doesn't really matter. All right, and then we just said that we need to be careful. We can't really use centimeters, so then your x is really 0.02 meters. I mean, they're the same number. We want it in meters, not centimeters. Okay, so then we need to find the kx squared. We need to find our k before we can plug this in. But we have a graph of force. So we already have our x for this length. So if we're looking at 5 centimeters, let's go to what force that would be. That would be a 3 Newton force. So then F equals kx. 3 newtons with spring constant k at a displacement of 0.02 or 2 centimeters from the relaxed length. How am I taking this over written down? That's going to give me a k of 150. And then now that I have k, I'm just straight plugging in. So this would be 1/2 k is 150, x is 0.02 squared, which gives me potential energy is 0.03 joules. I think this is the easiest way to do it. There's also a second way, which is kind of similar to what we were doing when we did work and energy. So we have a graph of force and distance, and we know that work is equal to force times displacement. So this would be just the area under my force distance graph. So if I'm going from equilibrium, which would be this point right here, to this compression, then this would give me the work done to the system. So work done would then be 3 times this distance is 2 centimeters, 2 centimeters, so 0.02 divided by the base, base and height divided by 2, because it's a triangle. So then if I do this, you're going to get exactly that your work is 0.03 joules. And if you're like, okay, but that's your work, Remember, the second definition of work is that it was the change in energy. In this case, you're changing the potential energy, so that would also give you your change in potential energy, which if it went from the equilibrium, there was no potential energy here, that would give me potential energy at that point. Or this is probably a little bit more straightforward. Oh, I can use the force in x to get k, and then plug in 1/2 kx squared. The thing you have to be careful with is, first of all, the centimeters, and also that this is my length, not my displacement x. You have to find it based on how far it is from equilibrium. Right, by how much? By how much does the spring's elastic potential energy increase if the spring is then compressed to from 5 centimeters to 4 centimeters? So I know this is my potential energy at 5 centimeters. If I go to 4 centimeters, then my displacement would be 3 centimeters, like even more, right? So just 0.03, technically a negative, but it's going to get squared anyway, so who really cares? And then my k, once I find it, is my k. I don't need to find it again. So my potential energy at 5 centimeters would be 1/2 150.03 squared, which is going to give me a potential energy of 0.0675, and this is at 5 centimeters. That's not my answer, because I didn't ask what would my new potential energy be at 5 centimeters. I asked how much would the potential energy increase from here to here. Well, if now I'm here, but I used to be here, how much it increased, you would just subtract. So 0.0675 minus 0.03 is going to give me a change of positive 0.0375 joules. If you wanted to get super fancy, the increase from 5 to 4 seconds would just be the area of just this piece right here, from here to here. And you could find this area pretty easily. You'd have to break it up, either do a trapezoid or break it up into this triangle and then the rectangle. Or you could just find new energy and subtract to find the difference. We have a mass of 5 kilograms attached to an unstretched spring of spring constant 500, so I've got M and K. It is released from rest and it oscillates up and down several times before it stops 10 centimeters. Let's go ahead and say that is 0.1 meters. Below its starting point, what is the change in potential energy of the mass spring Earth system? So it's tempting to just be like, ooh, spring, 1/2 kx squared, but we also are talking about it falling down, which is also gravitational potential energy, the MGH. So if you think about it, as this falls down, that means it's losing gravitational energy, but as you stretch the spring, you're storing you're storing spring potential energy in here. So we want to find what the difference in all of the potential energy is, so let's find the difference of each of these. So I know that I'm losing gravitational potential energy, so gravitational potential is just MGH, mass of 5, G will use 10, and then the height that it went down, like it lost 0.1 meters, right? You could think about it as negative, or you just leave it like you know that you're losing because it fell down. So then the change in gravitational energy is that it's losing 5 joules. And then we said that the spring energy is gaining because it's stretching, so it's storing more energy in the spring. That's 1/2 kx squared. And K was 500, and then the displacement from its rest or equilibrium position is just the 0.1 meters squared. So the change in spring potential energy is 2.5 joules, and it's gaining 2.5 joules because the more it's stretched out, the more energy it holds. So then if the system is losing this much gravitational and it's gaining this much spring potential energy, then overall it's losing -5, because losing 5 and gaining 2, I said losing -5. Overall, it's losing -5 and gaining 2.5, so it's losing 2.5 overall, which gives me C. Because I lost more than I gained, which is how I know this should be a negative. And I didn't just lose 5 because I also gained 2.5, so I only lost 2.5 in total. Alright, 19, we want to know the spring constant for the spring of this position versus time graph, and we know the mass is 12. So we can use period is 2 pi square root of m over k, because period is super easy. It's not exact here, but it's somewhere between 1.5 and 2. So like I'm gonna say 1.75. I'm actually not sure if it's like 1.75 or 1.8 or not. But when it's multiple choice and they're not that close, it's fine. 12 over k. Hopefully you guys can rearrange and you would get 1.55. The hesitation was for you to pause your video and do it on your own. Okay, we have a block attached to a spring on a horizontal table, negligible friction, negligible meaning we can ignore it. The spring is compressed from the equilibrium to the negative x position, released, and the mass will oscillate between negative x and x. Which of the following statements about the oscillatory motion are correct? The potential is the smallest at x. No, definitely not. Potential energy is 1/2 kx squared, so at x, the biggest displacement, it would be the greatest, so not true. The potential energy at x and negative x are equal. Yes, that would be true because you have 1/2 kx squared, 1/2 k negative x squared, but when you square this, it becomes positive, so you're getting the exact same value, both positive, so they are equal. Kinetic energy is smallest at the equilibrium position. Definitely not true. At equilibrium position, your x is 0, so potential energy is 0, which means you have all kinetic energy. So your kinetic energy actually is at a maximum at equilibrium. The kinetic energy at equilibrium is equal to the potential energy at x. That is true because at x, this is where you have all potential energy. At equilibrium, that's where you have all kinetic energy. So your total energy is potential here, whereas kinetic is your total energy here, and you know total energy is conserved, so this all potential has to be equal to the all kinetic here. A mass taking on a spring and vibrating up and down with a period that you could measure. You replace the spring with a spring that is twice the original spring constant, which of the following must be, what changes must occur in order for the period to stay the same. So we're talking about mass on a spring, and what we just did is we doubled the k. So if we were to leave this, you'd have 1 over root 2 times smaller, yeah, should be dividing. So I want to keep it the same, right? So I need something to balance out this, so that means you would want a 2 on top inside the square root, so doubling the mass and doubling k would just completely cancel out. So double the mass of the spring. Which of the following statements about a spring block oscillator in simple harmonic motion about its equilibrium point is false? The displacement is directly related to the acceleration. Well, we had already come up with the force over mass equation, so directly related. Yeah, bigger x is a bigger acceleration, so that's true. Acceleration and velocity always point in the same direction. That is not true. So if you think about it, like when this is pulled back here and released, at that point it's moving to the right and it has an acceleration to the right. So it is in the same direction, which is why it's getting faster. Then when it gets to this point, once it passes through equilibrium, it's still moving to the right, but now its acceleration is back towards equilibrium. These are in opposite directions, which is why it's then getting slower in this point when it then turns around. So the velocity and the acceleration are sometimes in the same direction, but not always. The acceleration vector is always towards equilibrium, yes, because your force is always trying to go back to equilibrium. Acceleration and displacement always point in opposite directions, yes, that is true, because when it's pushed to the left, when it is like compressed to the left, it feels a force back towards the right, equilibrium. When it's stretched to the right, it feels a force back towards equilibrium to the left. Simple pendulum, I have this mass on this string, and it has this period. If I want to have a period of 5 seconds, that is a longer period. So if you look at 2 pi square root of L over G, so if I want to get a bigger number, you can either decrease this number or increase this number. So I can either decrease the acceleration due to gravity or increase the length. So string replaced by a longer string. Large panda swings on a swing, creating a pendulum. During one of its oscillations, a baby koala bear crawls under the swing, and at its lowest point, the panda picks it up, which the following correctly describes and explains the change in the period of oscillation. So the period of oscillation for a pendulum is equal to 2 pi square root of L over G, my bad. I almost just did mass on a spring. This is an L. That doesn't look like L over G. So whenever he picks up the koala bear, what he's doing is he's changing the mass of the system, which does not have a period of an effect on the period. He hasn't changed the length of the pendulum, and it hasn't changed the acceleration due to gravity. So when I read this, I was like, C, and I was like, wait, I read part A, and I was like, some of the kinetic energy of the panda is transformed in the collision, so it doesn't swing as high. This part right here is completely true. We just did momentum collisions. This would be an inelastic collision where they stick together. So this one, right, this momentum is now, when he comes down here, is now shared between both masses, so he would be going slower, so that means he would not go as high. Totally true. But the amplitude, or how high it's going, doesn't affect the period, right? Where's it? We did it up here. We had ones where you kept the exact same period of oscillation, but it was going faster or slower, etc. So that is true. It does not go as high, which means it is going to go slower, but the period only depends on L and G, so the period would stay the same. 6 kilogram bowling ball is sliding at this velocity, so that's like your V naught. This is my mass. When it hits one end of a horizontal spring, and which is attached to a wall, the spring compresses this distance. You can call that like your amplitude. While stopping the ball, which of the following closely approximates the average force as it comes to a stop, meaning V final is 0. So we're looking for average force. There's 2 ways you can do this. You can use energy kinetic going into potential to find your K, and then use F average with Kx to find, Kx to find the F average. Or you can use work. I think work is actually a little bit easier here, because your work would be the change in energy. In this case, like the change in kinetic energy. How much kinetic energy you're doing comes from the work that the spring is doing. And remember, work is also Fd, so the average force that the spring is doing times this displacement, 0.77, would just be equal to the change in kinetic energy. Because it's going to 0, it's just the kinetic energy at the beginning. So that would be equal to 1/2 6 5 squared. And then you divide over, and you're going to get 97. Now, the second way to do this is if you use, this is potential energy, it's kinetic going into potential. So 1/2 mv squared goes into 1/2 k 0.77 squared. And then rearrange this, you get that your K is 253 newtons. The tricky part about this one is if you use this as your K, a lot of people would be tempted to be like, oh, well, my force is just Kx. That would be 253 times 0.77. And that would give me that my force is 194.8 newtons. The problem with this is that your force depends on X. That is my maximum force. At the very, very end, when it's finally compressed this distance, that would be the biggest force. But it had a smaller force all the way up until that, because we know that the force increases the more and more it gets compressed. Like if you were to draw a graph, and this is your force and this is your X right here for the displacement, at first it's not displaced at all, and then it's going to increase until it reaches the 0.77 when it has the 194.8 Newton force. So the average force in here is actually like somewhere in the middle, right? So if this is going up at a constant rate, which it would because it's just Kx. So then the average force is actually the biggest force divided by 2, which would give me 97. So that's why I used the work energy theorem, because it was easier to just find my average force as force times distance, and that would give me my change in kinetic energy. Okay.